Hello everyone and welcome back to the channel. This is Physics Junction with Mohammad Talha, and today this is this new video that we're doing as a part of all of our recent AS practice. So it's one of the most recent papers that we have available at this moment at the time of the making of this video, which is Winter 24 paper 22. Let's get right into it. So the first question, let's look at this. State what is meant by a vector quantity. Very straightforward. So a quantity that has direction and magnitude both, right? So another popular variant of this question, I think it was popular in this 2023 exam session, where the examiner used to ask a lot of questions in paper 1s in MCQs that what is meant by a physical quantity. So a physical quantity is something which has a magnitude and a unit, right? So if it says a quantity, that means that it's obviously a physical quantity, so it has to have a magnitude and a unit. So here what's additional is the direction. So it has a magnitude, but it also additionally has a direction, because a scalar quantity would also just have a magnitude. Part B, a sphere falls vertically through a liquid that has a density of 830 kg per meter cube. Sphere has radius r, constant velocity v as shown. Now in questions you must be picking up on this word, what this means. So constant velocity basically means, in the context of forces, that there is no acceleration, and by Newton's second law there is no resultant force either. So it says that the drag force D acting on the sphere is given by 6 pi r. This symbol is called eta v, where eta is a property of the liquid. Determine SI base units of eta. Okay, so it's up to you how you want to take it. I personally feel that in questions related to homogeneity, it's better to first solve both sides of the equation and then cross multiply, because there's a lot of simplifications you see if you just write it out before actually shifting anything anywhere. So D is a force. So force is mass times acceleration. So that's mass is in kg, acceleration is in meter per second square. So this on the left hand side is kg meter per second square. 6 pi, all of this is a constant, I can let this go. R is radius, so that's meter. I need to find the base units of eta, and v is speed, which is meter per second, and then here you have eta. Again, I'm still not going to cross multiply. First I'll simplify this as much as I can, and I feel like this is effective while trying to avoid errors. And once I have both of these simplified in a way that I can't really do anything else, that's when I start to cross multiply, which is kg meter per second square divided by that thing which was previously with okay, so this is eta, not v. Let me make that correction. So units of eta is what we're trying to find here. Divide by meter square per second. So this is m1. So kg remains kg m, and this is going to become 1 minus 2, which is minus 1, and s minus 2 minus minus 1 becomes minus 2 plus 1. So minus 2 plus 1 is also minus 1. So this becomes kg per meter per second. State an equation showing the relationship between the magnitudes of the weight W, drag force D, and upthrust U acting on the sphere. So as we said that it's falling at constant velocity, weight always acts downwards irrespective of how an object is moving. Similarly, upthrust always acts upwards irrespective of how an object is moving, but the drag force acts opposite to however the object is moving. So because this was falling vertically, so if it's moving down, then air resistance must be up, which is, sorry, not air resistance, the resistive force, in this case it's drag. So it becomes W equals U plus D. So that's what I write in the space for this answer. Volume of the sphere is given, drag force is 0.32, calculate the weight of the sphere. So it's obviously the sum of upthrust and the drag force. Drag force is given. I will need to find upthrust though. So weight equals U plus D. The formula for U is rho G delta V. Delta V means that this is the volume which is actually underneath the surface of the water. As we saw in the diagram, the entire sphere is below the water, so all of that volume is going to be plugged in here. So rho is the density of the liquid. Remember this as well. It's the density of the liquid, not of the solid. So that's 830. Small g is 9.81 and V is 4.6. This is cm cube. So just converting centimeter to meter is multiplication by 10 to the negative 2. Here it's 10 to the negative 2 cubed because we are converting cm cube to meter cube. So that's 10 to the negative 6 plus d, which is 0.32. So this turns out to be as a total, this is approximately 0.36 Newton to 2SF. Let's go on to the next question. Now this is definitely one of the more tricky questions of this one, not the first few parts, but the parts which come later. So the first part, define momentum. So that's the product of mass and velocity. Very straightforward. Next part, a child stands on a scooter on horizontal ground. Combined mass of the child and the scooter is 16 kg. Child starts from rest, pushes once on the ground with the foot, which causes her to accelerate. Push lasts for a time of 1.1 seconds. Speed of the child after the push is 0.6. Determine the average resultant force acting horizontally on the child and the scooter during the push. So the definition of force in terms of momentum is this. Right, and also there's an option here. You can also do this using F equals to ma. That's totally up to you. So change in momentum is final minus initial, because initially it started from rest, so there's no initial momentum. So the change is just equal to the final, because it would usually be Pf minus Pi. Here there's no Pi. Pi is 0, so it's just Pf, which is mass times final velocity divided by the time for which the force was applied, which was 1.1 seconds. And when you find this turns out to be 8.7 newtons to 2SF. Later, the child in B travels down a slope at a constant angle to the horizontal as shown in 2.1. At point A, her speed is 0.6 meters per second. She has a constant acceleration of 0.85 meter per second square parallel to the slope. After a time of 3.7 seconds, she reaches point B. Calculate the distance traveled by the child along the slope from A to B. So I think it's obvious here that you'll have to do this using equations of motion. And the biggest hint you could get is this: a constant acceleration, which is actually a prerequisite for using equations of motion. So I know that initial speed u is 0.6. I know acceleration is 0.85, right? And the time is 3.7. I need to find the distance, which is s. So it's obvious again that the equation that you have to use is ut plus half at square. U is 0.6 times t, which is 3.7, plus half into 0.85 into 3.7 squared, and then you find this out. So this turns out to be 8 meters. At point B, the child in C applies the brake with a constant force to maintain a constant velocity. So previously the child was accelerating down the slope. Now she applies the brake in such a way that there is a constant velocity throughout. And point C is 18 meters from point B as shown. Work done by the braking force is given. Determine the magnitude of the braking force. So I know the work done. I know the distance through which the force acts. So I can use the work done formula, which is force times displacement or distance in the direction of the force. So F would be W over S, which is going to be 250 over 18. This turns out to be 14 newtons to 2SF. Now this last part is why I said this question is good. is this. On 2.3, sketch the variation of the kinetic energy of the child and the scooter with the distance traveled from point A to point C. Numerical values are not required. So first of all, I know this, that x was basically, so the distance from A, x is what we just found here. So that's the distance from A to B, during which it was accelerating. And then from B to C, because this was constant velocity, so kinetic energy would also be constant. So I know for a fact that during this part, which is here, this will be a horizontal line, right? So this is something I know for sure. So distance is going to be, so with what do you call it? So kinetic energy is going to be constant with respect to distance. And I also know that from here to here, this is going to, so the speed is going to increase, right? But is it going to be a curve? Is it going to be a line? What is it going to be? And also, will this start from 0 or would this not start from 0? So we'll answer both of these questions one by one. First of all, I should think about it this way, that kinetic energy, the formula is half mv square. And because I know this was a case of constant acceleration, I can obviously use my equation of motion. And somehow I need to link this to distance. So what I can do is I can say that kinetic energy is actually half m, and instead of v square I can say this is u square plus 2as. And then this becomes half m u square plus half into 2as becomes just as. And this is kinetic energy. Now this is really important. It's a bit of math, but this is actually the only way to having a clarity of what we are supposed to do in this part. Kinetic energy is what's on your y-axis. S, the distance, is what's there on the x-axis. And if you look at this here, this is basically your y-intercept. This is y-intercept. And then A is basically the gradient. And this is how you get the straight line equation. So we end up finding this idea that it's supposed to be a straight line, but it's not supposed to start from the origin. And the reason it's not supposed to start from the origin is because we're plotting the variation of kinetic energy from point A. Was the child at rest at A? And the answer is no. So it wasn't at rest at A. So she had some kinetic energy there as well. And the value is going to increase from that point uniformly. So it's going to uniformly increase like this, and then it's going to become constant. Let's have a look at question number 3 now. So you have a stress strain graph which is given. In questions like these, it's important to look at the prefixes. So this is 10 to the 7 pascals, and this is percentage strain basically. Point E is the elastic limit of the metal. Use 3.1 to determine the Young modulus for P. So if you have to find the Young modulus, how would we go about doing this? So obviously we'll be using the linear portion of the graph. So we just need to pick up one coordinate. I think this looks pretty nice. This one, right? So at this is 12 into 10 to the 7. And the percentage strain is 0.5%. So I'll be using this coordinate to find the Young modulus. So Young modulus is FL over AX, or stress over strain, right? So this is basically percentage strain which is given. So that's 12 into 10 to the 7. And usually you would have strain which is extension over length. You just have that given as a percent. So in your calculation, you'll also just let the percentage go in there. So that's going to be 0.5, and that's going to be into the percentage sign, which is division by 100, or I can say multiplication by 10 to the negative 2. So this turns out to be 2.4 into 10 to the 10 pascals. This is exact. On the figure in line 3.1, draw a cross to show the limit of proportionality. Label this point Q. So the limit of proportionality is where your graph stops being a straight line and starts becoming a curve. Here it's this point. We have to mark this with a P. So that's that. Okay, we have to mark it with a Q. So let's draw a Q here. State the conditions necessary for an object to be in equilibrium. So we know that resultant force must be 0 and resultant moment must also be 0. You might also say this, that for example, for resultant moment being 0, you might also say that the principle of moments applies, and that's also fine. A wire is used to hold a uniform shelf AB horizontally in equilibrium as shown in 3.2. The wire is connected to the midpoint of shelf AB. Okay, so this shelf is uniform, right? And what this means here is that because this shelf is uniform, its center of gravity is going to be right at the center of this object. So it's going to be at the geometric center, right? So it's said that this wire is connected to the midpoint of shelf AB at an angle of 50 degrees to the horizontal. Shelf is attached to a wall by hinge at A. Length of the shelf AB is 0.65 and its weight is 33. So the weight would be marked from the center, which is also the point where the wire is connected, which is 33 newtons. Cup of weight 1.5 Newton rests on the shelf with its center of gravity at a horizontal distance of 0.12 meters from B. By taking moments about A, determine the tension in the wire. So there's also the tension in this wire, and the rule for marking tension is that it's marked away from the object being considered. So that's T, and if we resolve this, so that becomes T cos 50, because this is the component with the angle, and then the other one is T sin 50. So we have to take moments about A, so we can see that there's both of these which are acting along the same line, so I can actually subtract these, but not the other ones because they're at different distances. So the weight of the cup is 1.5 newtons, which is like this, right? So I can see that there's basically a clockwise moment like this, and there's going to be an anti-clockwise moment. So for this to actually be in equilibrium, because this was mentioned here, for this to be in equilibrium, the clockwise and anti-clockwise moments must be equal. So if I look at this, this is producing a clockwise moment, and then these two must be producing an anti-clockwise moment. And for this to produce an anti-clockwise moment, I conclude that T sin 50 must be more than 33. So I write it like this, that T sin 50 minus 33 times its distance, which is going to be half of 0.65, which is going to be 0.325, equals 1.5 times all of this distance, which is 0.65 minus 1.2. So 1.5 times 0.65 minus 0.12 is 0.53. So when you do this, so you multiply this, divide by 0.325, then add 33 and divide by sin 50. So T turns out to be approximately 46 newtons. Again, I'm not doing this in whole, just to speed this up right now. Stress in the wire is given, you need to find the radius. So stress is defined as the force acting perpendicular to that cross-sectional area. So force per unit cross-sectional area is what you would say. A is pi r square, so that's F over pi r square, because it has a circular cross-section. I need r, so that's going to be F over sigma pi root. So F over root of this, so F is the tension, which I just found out to be 46. To improve accuracy, you should use your calculator value, over sigma, which is 1.5 into 10 to the 7 into pi, and you take the root of this. So this turns out to be 9.9 into 10 to the negative 4 meters. More items are added to the shelf, doubling the stress in the wire. The wire is made of the metal from A. Use 3.1 to state and explain whether the wire will behave plastically or elastically as the stress doubles. So the stress in this case was 1.5 into 10 to the 7. Double of that would make it 3 into 10 to the 7. So 3 into 10 to the 7 is still going to be here, right? So yeah, because it hasn't exceeded the elastic limit, it will behave elastically. So yeah, so I would say that the new stress which is 3.0 into 10 to the 7 is less than the stress at the elastic limit. So it will behave plastically. Sorry, not plastically, elastically. That's question number 3. Let's have a look at this one. So question number 4, with reference to the direction of transfer of energy, compare the oscillations of transverse and longitudinal progressive waves. Now usually we could give this either with respect to transfer of energy or wave motion, but because the examiner has said with respect to the transfer of energy, so you have to use these exact words. And then if you write wave motion, even though it's technically correct, the examiner would not award marks for this. So you'll say that for transverse waves, the oscillations are perpendicular to the direction of transfer of energy, while they are parallel for longitudinal waves. So that's the first part. Part B, an open pipe. A pipe is open at one end and closed at the other end with a piston. Just reading this should trigger you to the idea that this is a question on stationary waves. This is also written here. And furthermore, you should know that this end is a node, this end is an antinode. The piston can slide freely and is at a distance of 4.5 into 10 to the negative 2 from the open end of the pipe. So you have the length of this. A loudspeaker is positioned near the open end of the pipe and emits a sound wave of a single constant frequency, and a stationary wave is set up as shown. On 4.1, draw a letter A at the position of an antinode. So I've done that beforehand. Speed of sound is given and we are asked for the frequency. So first of all, I'll need to find the wavelength. And if I look at this, I should know that for stationary waves, the node to node distance is half the wavelength. This is even half of that, so this is actually quarter of the wavelength. So lambda by 4 is 4.5 into 10 to the negative 2 meters. And from here, you'll find lambda. This turns out to be 0.18 meters. And I need the frequency, so for this, I'll use V equals to F lambda. So F would be equal to V over lambda, so that's 340 over 0.18. So 340 divided by this turns out to be, this is 1888, so I can say 1900 hertz. Next part. The piston is moved to the left. The frequency of the sound wave emitted by the loudspeaker is then changed so that a stationary wave is formed with the same number of antinodes as in 4.1. State and explain the change that is made to the frequency of the sound wave. So basically, we're talking about the first harmonic still, which is that if this is now moved to the left, so you have an increased length here, right? So the wave forming would probably be something like this. So like this, right? So you still have one antinode, one node, because it said that the number of antinodes are the same. So I can see here that the length has increased, and because the length has increased as per our calculations here, if the length goes up, then lambda is also going to go up, right? So if lambda is going to go up and if the speed of the wave is the same, then frequency must have decreased, right? So this is what you have to explain for this part. So you would say that the wavelength of sound is larger for this new stationary wave, so frequency must decrease. Since speed is constant, frequency must decrease. Let's go on to question number 5 now. Define electric potential difference. This is a question which is asked a lot, and it's the same as it used to be in O-level, so you still need to be able to ace this. So electric potential difference, I write it in terms of work done. So this is the work done by a unit charge in moving across a component Another possible definition is in terms of energy transferred. So you would say energy transferred per unit charge in so energy transferred per unit charge from electrical to other forms, right? With EMF, it would be the reverse. In that case, it would be the work done on a unit charge by the source for the entire circuit. And in terms of energy, it would be the energy transferred per unit charge from chemical to electrical forms. Let's have a look at this question now. Part B, a power supply, 3 resistors, component X are connected in the circuit shown in 5.1. Power supply has an EMF of 230 volts, negligible internal resistance. Current in the power supply is 7 amperes. Identify component X. So this is the circuit symbol for a heater. Show that the potential difference across the resistor of 0.86 ohms is 6 volts. So the potential difference across this we must show is 6 volts. That's really easy because I know the current through this, I know its resistance. So I can just use V equals to IR. And because it's this easy, this is for just 1 mark. So this is 0.86 is the resistance and the current was 7. So 0.86 times 7, that's approximately equal to 6 volts. Determine the current I1. Now for the current I1, let's see. So I know that the potential difference across this resistor is 6 volts. And now I can also imagine that this is basically in series. So if there's 6 volts here, so there's 224, 230 minus 6 appearing across here, appearing across here. So I don't know resistance X, but I can find out I2 first, right? So I can just do 224 divided by 170. That's going to give me I2. So I2 is going to be 230 minus 6, which is 224 over 170. So this turns out to be this is 1.3176, so 1.32 amperes, and then I1 by KCL, because 7 is flowing into here and then that's splitting up into I1 and I2, so that would just be 7 minus I2. So that's 7 minus 1.32, 7 minus 1.32, that is equal to 5.68. So I can say that's 5.7 amperes. So that's this part. Let's go on. Calculate the potential difference across component X. So now that I know I1, I know that this is the current flowing, which was 5.7, and I know that the potential difference across here is 224, right? So I know that the sum of this drop plus this drop is going to be equal to, what do you call it? 224, right? So I can just do I times 2.4 plus X, because both of these are in series, equals 224. So I1 is 5.7 times X plus that other resistance is 224. What was that other resistance? That was 2.4 ohms. So this is 2.4. And from here we can find X. So this is going to be 224 divided by 5.7. That is 39.2 something minus 2.4. So this turns out to be 36.89. So I can say 37 ohms. Sorry, not 37 ohms, 37. Oh, okay, my bad. So actually we just had to find the resistance, right? So I can just do this instead of doing this. What I've just found is the resistance, right? So it's better that if I do it like this, that so 5.7 times 2.4 is going to be the voltage across that plus the voltage across X. So this is 5.7 times 2.4. And then you just take it to the other side and subtract, right? So voltage across that small resistance, if you subtract that from 224, you will get the voltage across X, which turns out to be 210 volts. Calculate the power dissipated in component X. So for the power, I know the current through the component X, the heater, and I know the voltage across it. So potential difference is 210. Current through X was I1, right? So that's 5.7. Again, for accuracy, I should use my calculator value. I'm just writing this here, but in fact, I'm using my calculator value. So this turns out to be 1200 watts. The purpose of this circuit is to provide power to component X, determine the percentage efficiency of the circuit. So we know the input power is basically going to be the power supplied by the battery. So it's power output over power input times 100, because it's clearly asking for percentage efficiency. So output is 1200. Input is 230 was the input voltage. Current supplied was 7, right? So 1200 over 230 times 7 multiplied by 100. So this turns out to be approximately 75%. Part 7, this one. The resistor of resistance 170 ohm is removed, leaving an open circuit in the lower branch of the circuit. There is no change to the resistance of component X. State whether the current in the power supply increases, decreases, or remains the same. So open circuit means that basically there's no resistance there, right? So there's infinite resistance. So this just goes away. And you can imagine that this is like an open switch right now. So there's nothing in the center. So that means that this resistance has now gone away, right? So obviously no current will flow through this, all current just goes through this. And it was asking for the change to the power, the current produced. So I can say that now the resistance has increased. Why? Because whenever you attach a resistor in parallel, the total resistance goes down. Now you've basically removed this. So the resistance increases, and that's why the current is going to decrease. So the current decreases. All right, don't think about it in this way, that it's the same amount of current that would be supplied whether this would be here or this would not, because the current supplied is dependent on the resistance being faced by this supply. So because the resistance has now gone up because of the removal of this, your current goes down. Let's go on. Compare an alpha particle with a beta positive particle in terms of their masses and charges. Very obvious. So mass of alpha is much greater then the mass of beta positive, right? It's just comparisons. So mass of alpha is 4u, right? Where u is 1.66 into 10 to the negative 27. Beta is basically, as far as mass is concerned, with regards to charge, both of these are positively charged. So I'll say that both are positively charged, but the charge of alpha is twice the charge of beta, beta positive. Next, nucleus P undergoes alpha decay to form nucleus Q. Nucleus Q then undergoes a further decay to form R. Proton and nucleon numbers of P and R are shown in 6.1. And then we have to basically, in this next part on 6.1, draw a cross X to show the proton number and nucleon number of Q. Label your cross Q. Okay, so P to Q is alpha, right? So P to Q, I know that the nucleon number is going to decrease by 4. So it's going to become 212. And then the proton number is also going to decrease by 2. So 84 minus 2, this is Q. And then I'm pretty sure the next part would ask what is this type of decay in which it's going from Q to R. So the proton number is increasing by 1. So this must be beta negative. So state the names of the particles emitted as Q decays to R. So one of these would be the electron because of beta negative, and the antineutrino. Right, so these are both the leptons emitted here. Before the alpha decay, P is traveling at a constant velocity. After the decay, Q has a velocity of 1.3 into 10 to the 5 at an angle of 68 degrees to the original path of P. Alpha particle has a velocity of this much at an angle theta to the original path of P as shown. Use the principle of conservation of momentum to determine theta. Alright, so previously there is no vertical velocity, so I can say that afterwards as well there must be no vertical velocity. So what is the momentum of this must also be the momentum of this vertically. So this one is going to be 150 into 10 to the 5 sine theta. This is just the velocity. And this one would be 1.3 into 10 to the 5 sine 68. But then there will also obviously be the masses. So for alpha, I know the mass is going to be 4u, right? The atomic mass unit. And Q is something I did talk about here. So Q has a mass of 212u, right? So this is a mass of 212u. Conservation of momentum. So I'll say this, that 4u into 150 into 10 to the 5 sine theta equals to 212u into 1.3 into 10 to the 5 sine 68. No need to go to the data sheet because the u's cancel out anyway. And then you basically just multiply this. So 4 into 150 into 10 to the 5 this is 6.0 into 10 to the 7 sine theta equals 212 into 1.3 into 1.3 into 10 to the 5 into sine 68. This is 2.56 into 10 to the 7. These cancel out as well. So it's sine inverse of 2.56 over 6, which turns out to be approximately 25 degrees to 2SF. Calculate the kinetic energy of the alpha particle. Now for this, you will need to go to the data sheet if you don't have the value of U memorized. So kinetic energy half mv square. So half alpha particle is 4U. The value of U is 1.66 into 10 to the negative 27. And the speed of the alpha particle was 1.5 into 10 to the 7, right? Or 115 to 10 to the 5. 1.5 into 10 to the 7. Don't forget to square this. A lot of people do forget this. And then you multiply. So this turns out to be 7.5 into 10 to the negative 13 joules. And that is basically this entire paper. Like this video, comment if you have any suggestions on something else that you would like to see. Share this with your friends, whoever may benefit from this, and subscribe to the channel for more amazing content like this. And there will be a lot of that coming up soon before your papers. So best of luck, and I'll see you next time.